Right. Total energy is equal to 1 by 2m x naught square omega square. Now this x naught is the maximum displacement, which is also called amplitude. So we can write energy total in the simple harmonic motion is 1 by 2m amplitude square and omega square. This omega depends on g, it depends on L, it depends on K material constant, it depends on the mass. So this omega is constant, m constant, half constant. So energy in oscillation is directly proportional to amplitude square. We have done when this energy is lost by any oscillating system, it has direct effect on the object amplitude. So amplitude also decreases and it is known as damping. In the previous lecture, we have done this. Now suppose energy directly proportional to amplitude, energy is gained by the object, so the direct effect on the amplitude, it increases. When energy is absorbed by any oscillating system, its amplitude increases, and this increase in the amplitude, increase in amplitude due to gain of energy in physics is called resonance. So this is opposite to damping. So today we have to study this resonance. Now there are a few conditions for the resonance. Number one system must be free oscillation system. So what is free oscillation? An oscillation in which no energy from external source is required to maintain its amplitude. Yes, energy is required, but no energy from the external source is required to maintain its amplitude. Mean it does not gain any energy from the external source to maintain its amplitude. So this is called free oscillation, or it is called free oscillating system. Number two, forced oscillation. Now, this is the oscillation. An oscillation which requires energy from external sources to maintain its amplitude is called forced oscillating system. Now the third, what is oscillation? If the question is what is oscillation? To and fro motion of an object about a fixed point is called an oscillation. Okay, now this force oscillation sometimes is known as damped oscillation, and this free oscillation is sometimes called undamped oscillation. Now, when frequency of any externally driven system becomes equal to frequency of any naturally oscillating system, then energy is absorbed by natural system from external system which results in increase in amplitude of natural system. So this is very, very important for the resonance. So when the frequency of externally driven system matches the frequency of the naturally oscillating system, the natural oscillating system absorbs energy and increases its amplitude. This is called resonance. And this is similar to the AS waves. When the frequency of the one wave becomes equal to the frequency of the second, both are called coherent, and this is the good condition for interference. So in constructive interference, amplitude increases. It's similar like that. So when natural oscillating system absorbs energy, when it will absorb energy? When the frequency of the external system becomes equal to the frequency of the natural system. Mean we are not changing the frequency of the natural system. We are changing the frequency of the externally driven system. By changing the frequency of externally system, right? We can match it with the frequency of the natural system. The natural system will absorb energy from the external and the amplitude of the natural system will increase. This phenomena is called resonance, and this resonance is used in microwave oven cooking. Number two, it is used in radio or TV tuning circuits. Number three, it is also used in NMRI, which is called magnetic resonance imaging. So resonance is useful in these microwave oven cooking, radio tuning circuits, and MRI, magnetic resonance imaging. But it is avoided, number one, vital organs in human body. Resonance is avoided. If the body part, vital body parts, vital organs resonate with the external system, so then there will be a problem. Number two, it is avoided during earthquake. The resonance of buildings is avoided during earthquake. Otherwise, the building will fall. And number three, it is also avoided in windows, bridges. Resonance of bridges, windows is avoided during thunderstorm. So, three examples in which it's useful, and three examples in which we have to avoid it, otherwise there will be a problem. So the next is graphs of resonance. Now suppose at the y-axis, amplitude, at the x-axis is the frequency in hertz. So this is the frequency of the externally driven system. When it is switched on, it starts from 0, gradually it increases. And this is the amplitude of the naturally oscillating system. Initially, when the external system is switched off, object is oscillating with certain natural amplitude. So this is the natural amplitude. Now, suppose somewhere here, the frequency of the external system matches with the frequency of the natural oscillating system. When you are increasing the frequency of the external system, and it becomes exactly equal to the naturally driven system, right? Then what will happen? The amplitude of the naturally oscillating system increases. If it is undamped system means it's not losing any energy, then the increase in the amplitude will be infinity. When the frequency of the external system increases from this value, so there will be mismatching of the frequency, then the frequency of the undamped system will decrease, and gradually it becomes equal to the previous natural frequency. So this is the resonance of undamped system. Now, if the question is, the system is light damped, then the amplitude, yes, increases to a certain limit, but when increase in energy rate, mean the rate of increase of the energy becomes equal to the rate of loss of energy, then there is no further increase in the amplitude, because when the amplitude is increasing in the light dense system, right, its kinetic energy increasing, air resistance increasing, so the loss is increasing. So when rate of gain of energy becomes equal to the rate of loss of energy in the light dense system, further no increase in the amplitude, so it stops here. But when the frequency increases, it comes back to its original value. So this is the resonance for the light damped system. This is light damped. And this is undamped. Next, if the system is heavily damped, then this is a graph. So this is the resonance for heavy damping. Heavy damped system. So very small amplitude will increase because there is a big loss of the energy by the heavily damped system. Okay, now this is a resonance when the frequency of external system exactly equal to F naught. And this is called complete resonance. But sometimes when frequency of the external system is half of the resonant frequency, half of F naught, or external frequency is equal to double of the F naught, then the wave shape will be like this. Look, this is the frequency. And the second frequency is this. Suppose this is the frequency which is double. Now look at this point, 1 and 2. So number 1 and number 2, they are not exactly all the time in phase, but at point 1 and point 2, they are partially in phase. They are partially coherent. So there will be partial resonance. Mean the resonance will be for the short interval of time, and then frequency mismatches, it stops. So when the frequency of the external system double the natural frequency or half the natural frequency after every 2 oscillations, both systems will be in phase for a short period of time. There will be resonance. Or short interval. And known as partial resonance.